with these B1, B2, B3.
But there's like 16 bits in the.
Right, this is just a smaller example.
Okay.
Oh, I'm sorry. Okay, this is a 3-bit DAC. Normally you have 16, 21, or 24-bit DACs. Sometimes you might
So
have
this
8.
thing like doesn't really exist.
Correct. This is just for learning. I'm so sorry.
You use them for non-audio
Okay.
too.
Yeah, you might use them to encode a signal that's not audio.
Yeah.
This might exist, and in fact, 1-bit and 2-bit DACs are leveraged for the other technique we'll talk about. But this app is just
Like
an example.
if
You
you
can
want
easily understand it.
if you want to do something with like LEDs, you could use this to like turn them on and off or something like that, and change
Right.
the
Right, yeah, you can change the color of an LED like this or something like that.
It's just
Anyways,
really
so
simple.
So
but I
only
think there
one
might have been questions.
bit.
Can someone check that one?
So only one bit is being input at a time.
No,
yeah,
so
the
you'll
16
change out all of these bits to, so I'm gonna draw on the
So
chalk.
they all go to 0 and then one of them goes to 1.
So if we have, this is our wave, we have a 4-bit DAC. Each one of these maps to B. So this is B1, this is B4, okay? And as instantaneously, we're just talking about one frame of our sampling rate here. Sorry to the people who are online who can't see me right now. But we'll go outwards like this, and there's resistors in here and in between that will actually compound to make this bit worth less compared to this bit as far as the voltage added to the output signal. Does this make sense? So we'll apply instantaneously, not talking about changing these at all yet. We'll apply 1, 0, 1, 0. So B1 will gain 1. This is actually a reverse binary. So this is the least significant bit. So if we were writing this in real binary, it would be 1, 0, 1, 0. Where this is the most significant, this is the least significant. We've reversed it because we want this to be the least significant bit. So B1 in our diagram for the people online is the least significant bit, and B3 is the most significant. Because B3 will apply the most voltage to the output, and voltage is the amplitude of the wave.
So like,
Okay?
so on like the previous slide, we have like those 16 bits. It's like the steps basically.
Yep. Yep.
At each second, there's only one value
Right.
out of that 16-bit range that's being inputted to this DAC thing.
Right. Exactly.
So on your you have 101 or 1010.
Yep.
Wouldn't there only be one at a time?
So the idea is we're looking at the top picture, and it's a 16-bit approximation. So each one of these steps is a different value, and you can like this step here is like 2. So that's what 8, 9. That's 9. So
So you
the
just
value is
you just
9.
like feed it in and like it just basically it's like
Yeah.
it's like RNA or whatever that thing.
It's like the
biology.
No.
We
I know
just
you're talking
feed it
about
in.
the zipper.
Yeah, the
Yeah, I
zipper.
know what you're talking
Okay,
about.
so
Yeah.
well, that waveform is say 5 volts, and each of your signals coming in are 5 volts, but in order to convert that to a range from 0 to 5, not binary but analog, you split the LSB 4 times, say in this example, and the second to last 2 times, and the most 1
Right.
time.
Yep. Exactly.
So that you can get that modularity, so you can get different steps in the voltage. So they're taking for each split second. So each of those little steps in the pulse wave, they're saying, hey, the binary value of this analog value is, say, 10 in binary.
Right.
So they're just converting that back into an analog voltage.
Right.
Oh, so every single step's height can be represented as those bits, those minutes.
Right. Exactly. So
So
this.
that entire chunk right there is one step.
Yeah, and the
Yes.
more
This
bits
is
you
literally one level. So for the people online, the binary number that we would put into these bits is the same value as is at one of these steps at any instantaneous time. And then at our sample rate, which in this case is 44.1 thousand times per second, we will change those numbers being output. So you need the ability to change the numbers really fast, which are being output to the bits, and you need the ability to then have a very accurate set of resistors that make it so that each one of these bits is applying exactly the right amount of current. So the reason that these aren't used is because they're very expensive and difficult to source. So these DACs that work like this, if you have a question, please definitely ask it before we start to move on here. These DACs are very expensive and nobody wants to make them because you have to source, for a 16-bit DAC, you need 16 2R resistors and 16 or so R resistors, or I guess 17 R resistors, and they have to be perfect. They have to be within microns precision. You need lasers to cut these. Like, they need to be so perfect. If they are off at all, you have completely, like the DAC won't be linear. It won't be able to represent a bit as well as it should. So if there's a problem with this 2R resistor, right, then this bit, this last bit, the B1, is going to have more or less current applied to the output than it should. Does that make sense? So if one of the resistors in the chain isn't right, it means that the voltage that's going to be output is not exactly what we want it to be. Yeah? Making sense? How about for you? Is this making sense for you? I know you walked in a little bit late, so I want to make sure that you caught up.
That's somewhat from what you're saying so far is, well, like, if you have all these potential like risks, I guess you could say, like, what's the benefit of using it?
So the benefit of using this is that if you can get it right, it's A, super simple, and B, it uses no approximation. It simply encodes it right. When we talk about the other method, you'll see that they're honestly literally guessing. And they're tailoring their guess over time into something that they believe is the right thing. However, this, you get the right waveform. As long as these are precise, you are getting exactly what is represented in those bits put out to the analog signal. So it's very precise. Audiophiles generally really like this. There's a big debate as to whether it's worth it. I bought into it. That is a multi-bit DAC right there. It's actually not that expensive relative to how this used to be, let's say 5 or 10 years ago. It's $500 or $600 versus like 5 or 10 years ago, we would have been looking at like tens of thousands to be able to get this kind of precision in these resistors. Another problem with this is that these DACs are very sensitive to temperature. These resistors are almost definitely not going to be linear in their representation of their resistance over different temperatures. So as the temperature goes up, the resistor's ability to maintain its exact resistance is going to change. So like if this is our temperature, this is our resistance, this is temperature, this is resistance, then the resistance is going to change based off the temperature. It might go up, it might go down, depending on the material. And that's another thing you have to deal with. So a lot of times they'll use a certain like heating element to make sure that the board is like at a specific temperature, because these are so sensitive. They're like little crybabies. You can't get them to do what you want. But when you do, it sounds amazing. So this is one of the cool things that like most of the time you won't run into, but it's really simple. And once you understand this, it makes it a lot easier to kind of understand a little bit more about what's going on. Okay, we're doing okay on time, but I gotta start going. So now we're gonna get to delta signal modulation. I'm gonna talk about this a little bit more when we get into the amplifiers that also leverage this stuff. But essentially, what you need to know is this is what's used the most. It's the cheapest thing to manufacture. You only have to match a couple of resistors. And most of the work is digital because it's taking integrals of waves and differences and it's doing math to approximate the waveform over time. And the way it does that is by running the sampling, running at a significantly higher speed than the sampling rate and doing something called oversampling. Oversampling is when you have so much time between when you need to output your next change in the wave that you're able to make the approximation, let's say like 40 times. So you're running at 40 times the speed of the sampling rate. So if the sampling rate is 44.1, you're at 40 times that, and you're able to actually do 40 different approximations to get the best approximation you can, and then output that. You run faster, but for our technology, that's not a problem. We can get a clock rate that's that high. So this is definitely not as in-depth, and we're going to get a little bit more in-depth as we go on. We're going to talk about showing how the waves actually work, and how they're actually converted and amplified. I have some more pictures that will make more sense, but basically, to do this, you only need to do one bit. You only need one bit because you're actually using the pulse width modulation that we saw earlier to create an approximation for the wave, and then at the end, you take that pulse width that you get and you run it through a simple filter that we'll look at, and it will make an analog wave like really perfectly. It's super weird. But we'll look at this more in a second. It's what is in everything you use. It's in your phone. It's in nearly every single DAC you already uses this technique. And it will make more sense when we look at how it changes the waveform from digital later on. Okay, right now. So this is actually, I'm going to show you two ways to get a waveform from a pulse width modulated waveform. So you have a digital pulse width modulated waveform and an analog pulse width modulated waveform. What the difference between those two things is, one is at a set voltage. So let's say line level is 2 volts. So your USB transmits a digital signal at a specific voltage. You can also do it analog by changing the voltage. So what I mean by that is, you see PWM signal 1 and 0. You can change how high the 1 is if you wanted to do it in analog. That'll be important in a moment when we look at how the Class D amplifier works. I just want to make sure that when we're here we address that. So right now, talking about the digital version of this with a very set 1 line level, 2 volts. So the 1 is at 2 volts all the time. We can always assume that. We're considering it to be digital. Now it's just zeros and ones like we talked about before. So now we're looking at, this is the simplest way, or one of the simplest ways, to take a sine wave and get this pulse width modulation. So if you have a sine wave, you can actually convert to this pulse width modulation by applying a sawtooth wave over the analog wave. So you see how the blue wave is placed on top of the red. Now every place that your blue wave is lower than the red wave, you turn on your pulse width modulation. So you can see between this point and this point here, the pulse width is on, and even has nice lines to show you, because the blue wave is under the red wave. Okay? And then when it's over the red wave, we can see that the pulse width modulation wave is off. It's 0. So we're taking an analog signal and getting a digital signal by applying this filter. This is one type of pulse width modulation. It's not what is generally used, but it is a very simple way to do it. Does this make sense?